Today we introduce two fundamental quantities that characterize signals: energy and power. For a discrete time signal x of n, the total energy is defined as Ex equals the sum from n equals negative infinity to positive infinity of x squared of n. The average power is Px equals the limit as m approaches infinity of 1 over 2m plus 1 times the sum from n equals negative m to m of x squared of n. For periodic signals with period n, the energy is always infinite, and the power simplifies to 1 over n times the sum from n equals 0 to n minus 1 of x squared of n. Let's see two contrasting examples. First, consider the finite signal x of n equals -1, 1, 0, 2, -1. Its energy is 1 squared plus 1 squared plus 0 squared plus 2 squared plus 1 squared, which equals 7. Since the signal has finite duration, its power is the limit of 7 over 2m plus 1 as m goes to infinity, which equals 0. Now consider x of n equals the unit step u of n. The energy is 1 squared summed infinitely, so Ex equals infinity. For the power, note that u squared of n equals u of n, so we sum m plus 1 ones from n equals 0 to m. This gives the limit of m plus 1 over 2m plus 1, which equals 1/2. These examples illustrate two categories. An energy signal has finite energy and zero average power, like our 5-sample signal with Ex equals 7 and Px equals 0. A power signal has infinite energy, but finite non-zero average power, like the unit step with Ex equals infinity and Px equals 1/2. Every signal falls into one of three classes: energy signal, power signal, or neither. Periodic signals are always power signals because they repeat forever, accumulating infinite energy but maintaining finite average power. For continuous time signals, the definitions use integrals instead of sums. The energy is Ex equals the limit as b goes to infinity of the integral from -b over 2 to b over 2 of x squared of t dt. The power is Px equals the limit as b goes to infinity of 1 over b times the same integral. For periodic signals with period t, the power is Px equals 1 over t times the integral from -t over 2 to t over 2 of x squared of t dt. The root mean square value, or RMS, is simply the square root of the average power. PRMS equals the square root of Px. Let's derive the RMS value of a sinusoidal signal x of t equals a sine of 2 pi ft. This signal is periodic with period t equals 1 over f. The power is 1 over t times the integral of a squared sine squared of 2 pi ft dt over 1 period. Using the half-angle identity, sine squared theta equals 1 minus cosine 2 theta divided by 2, we separate the integral into two parts. The integral of cosine over a full period equals 0, so we are left with a squared over 2t times t, which equals a squared over 2. Therefore, the RMS value is a divided by the square root of 2. Here are two practical applications. First, the European mains voltage is described by V of t equals 220 times the square root of 2 times sine of 2 pi times 50t volts. The peak amplitude is 220 root 2, so the RMS voltage is 220 root 2 divided by root 2, which equals 220 volts. That's why we call it 220 volt power. Second, consider a decaying exponential. X of t equals e to the negative alpha t times u of t with alpha greater than 0. Its energy is the integral from 0 to infinity of e to the negative 2 alpha t dt, which evaluates to 1 over 2 alpha. Since energy is finite, the power is 0. This is a CT energy signal. Today we covered signal energy and power for both discrete and continuous time. Energy signals have finite energy and 0 power. Examples include finite duration dt signals and decaying exponentials. Power signals have infinite energy but finite non-zero power. Examples include periodic signals and the unit step. The RMS value of a sinusoidal signal is always a over root 2. In the next lesson, we'll explore systems and their key properties: causality, memory, linearity, time invariance, stability, and invertibility.